right, welcome to the Future Grid with Buildings and EV session. So many of you have been coming to Best Center's National Institute every year. This is the first time we are adding an EV-related session because EV numbers have been growing in many parts of the country, catching many large utilities' attention. And both from a how do I handle the load growth from EV charging standpoint, as well as how do I leverage EV charging as one of the most valuable grid resource standpoint. If EV charging is managed well, it can really help improve energy affordability, grid reliability, and decarbonization, which is important goals for many utilities and jurisdictions. There's increasing interactions between buildings and EV charging because they are often connected load, and it's no longer a science fiction to send power back from EV battery to the grid. It has been demonstrated in multiple pilots all around the country. So some of you are building science engineering educators. We are here to help you start thinking about how to incorporate state-of-the-art EV charging technologies into teaching and workforce training. So I'm very excited to address this emerging topic with 4 industry leaders here with me today. We have one leading utility, PG&E, here in California, and 3 technology innovators covering residential and commercial sectors to share their vision, their program innovations, technology solutions, and their experience in the field with you today. I also want to mention, if you want to learn more about this EV charging landscape, this space, there's also a lab report, which I'll put into the chat so that everyone can reference to get more background on this topic. So with that, I will introduce our first speaker, Sarah Sweetheart, Vehicle Grid Integration Manager from PG&E. Welcome, Sarah.
Thank you, Jingjing. Good morning, everybody. I will share my slides. All right. Hopefully you can see. So as Jingjing mentioned, I am the manager of the Vehicle Grid Integration team at PG&E. I sit within a broader team called the Clean Energy Transportation team, and we are focused all around the potential of EVs. There is a growing EV adoption in California, especially. About 1 in 7 EVs are sold in California. And we're expecting that growing EV adoption to contribute to about 70% of electric load growth over the next 20 years. So an extreme amount of load growth coming from electric vehicles. You can see kind of from 2017, that chart ends in 2020, but the huge hockey stick curve of EV adoption in PG&E service territory, we are currently at over 675,000 EVs registered in our service territory as of October 2024. So a lot of vehicles driving around, charging, connected to our grid. Jingjing mentioned this, but why does the utility care about EVs? Well, one, we are transitioning to becoming the transportation fuel provider as more electric vehicles are driving around our service territory. But we also believe that if properly managed, EVs can provide that triple value stack of reliability, helping reduce peaks on the grid, resiliency, provide backup power to customers' homes, buildings, microgrids in the event of outages, and then decarbonization. So cleaning up the transportation sector by transitioning the fuel to electricity, but also especially with the ability to export power from vehicles that could replace some natural gas peaker plants, so further decarbonizing the electric sector. We have developed a strategy around EVs called our True North strategy. We want to support connecting 3 million EVs to our system by 2030. So we still have a lot of growth given that 675,000, but we're optimistic that we will reach the 3 million vehicle goal by 2030. That's both residential and commercial and fleet customers. And then what I want to focus on today and where my team really focuses is, okay, once those EVs are driving around and they're charging, how do we leverage these batteries on wheels to serve the grid and better serve the customer? And so the way that we talk about the kind of value that EVs can provide to the utility is in the term flexible load. So load that can be shifted around. And we have a goal of 500 megawatts from EVs through vehicle grid integration by 2030. So vehicle grid integration is the kind of umbrella term we use to talk about integrating EVs and their charging and discharging or charging and exporting of power to the grid. And how we define it as PG&E is that a vehicle participating in VGI means altering the time, so time of day or time during the year, the charge level, so the amount of kWs that a vehicle is using, or the location, the geographic location, which grid-connected EVs charge or discharge. And the reason why that's important is that the grid has different needs based on time of day, time of year, and geographic location. And so having EVs as a more flexible load source, we want to be able to send signals to have the EVs shift their charging to the middle of the day to soak up some excess renewables, or export from 4 to 9 p.m. to help reduce and shave the system peak. So that's kind of our ultimate goal and how we define a vehicle participating in VGI. We further break down VGI into 3 buckets. I'll start first with, there's a lot of acronyms, but hopefully I've defined them appropriately on the slide. V1G is normal charging, so a unidirectional power flow. The vehicle plugs in and the power comes from the grid to the vehicle. The way that we can alter the time or location that EVs are charging or discharging, one strategy is through rates. So I think everyone is pretty familiar with this, but you send a kind of static price signal to encourage customers to charge their EVs at certain times during the day. For example, time of use rates in California encourage charging overnight when the price of electricity is low, and discourage charging by increasing the price of electricity from 4 to 9 p.m. So rates can send those price signals. The second way to encourage the charging at the right times and right location is a term called managed charging. And that just means kind of direct control of the vehicle's charging, either through the vehicle itself, the charger, or third-party software that can respond to signals, whether that's a specific program that the utility is offering, or just customer preferences. That software can then indicate when a vehicle should be charging or not charging. And then the last category gets at the bidirectional flow of energy. And so that's a term we use, vehicle to everything, V to X. So power that can be exported from the vehicle to serve a specific load, a home, a building, or exported to the grid as a generation source. So kind of 2 distinct areas of talking. There's opportunities in just the unidirectional flow of power, and then there's opportunities as we talk about the bidirectional flow of power. So from PG&E's perspective, where do we want to go? Our grid needs have changed and will continue to change. I don't know how many of you are familiar with this duck curve concept, but in general, there's a very low demand for power in the middle of the day, and then it ramps up in the 4 to 9 p.m. As everyone gets home, turns on their appliances, uses their power. So that's kind of the demand curve, and it looks a bit like a belly of a duck all the way up to the head. And then when we look at the supply of power, especially in California with a high penetration of renewables like solar, there's actually, let's take the summer months, there's a huge amount of supply in the middle of the day, but then solar ramps down at night. And so there's a little bit of a mismatch between the demand for power and the supply of power on our system. And so what we want to do is leverage the flexibility of EVs. Usually people have some flexibility for when they can charge their vehicle, maybe as long as it's ready by the next morning at 8 a.m., but it doesn't matter the previous hours that they charge. And so we want to leverage the flexibility of that load to help soak up some of that excess renewable in the middle of the day, and then discharge in the peak hours and the evening hours to help reduce the system peak, and just be able to respond to specific signals, whether that's on like a local transformer or just broadly on the PG&E system. So some of the activities that we're doing to achieve that ideal state, I've listed here 4 of our current VGI pilots. I'll run through them pretty quickly and then hit on 2 in more detail. So we have a V1G pilot called EV Charge Manager with WeaveGrid. This is focused on 3 counties, Santa Clara, Alameda, and Contra Costa County, with a target of enrolling 7,500 customers into a managed charging program. So customers enroll, they get a participation incentive, and signals from the utility are sent via WeaveGrid for them to charge at different times that are beneficial to the grid. This pilot is particularly focused on looking at individual transformers and making sure that the load at that individual transformer is not spiking, or we're not overloading that transformer. I think John will also get into some more detail about that pilot. We then have 3 V2X pilots, so that's focused on the bidirectional aspect of electric vehicles. One is serving residential customers, one is commercial customers, and one is focused on integrating EVs with microgrids. And the idea here is providing incentives for the costly V2X hardware, and then testing some use cases. So we're testing the ability of these systems to provide backup power to the home in the event of an outage. And then we're also enrolling these customers on an hourly flex pricing, a dynamic rate that if they export power from their vehicle, they will be compensated for it. So getting at that ability of the vehicles to export power, and then incentivizing customers to participate by compensating them for it. We also have partnerships with specific OEMs like Ford and General Motors. And then, as I mentioned before, rates is one of our key strategies, but there's some elements like submetering and real-time pricing that we're also exploring. So I think I'll wrap up with just a quick overview of 2 of those pilots. So this one is more detail on that EV Charge Manager pilot focused on managed charging. This is looking at single family homes. So residential homes, a customer installs a level 2 charger, and then with certain vehicles and charging equipment, they enroll with WeaveGrid to have their EV charging load managed and respond to specific grid signals. This is kind of a first of its kind pilot for PG&E focused on the distribution system instead of just responding to general time of use price signals. We're really focused on, okay, at this specific transformer, if there are 4 EVs, can we optimize and orchestrate their charging to kind of flatten the load and make sure that we're not overloading that particular asset. This pilot will run through the end of 2025, and as I mentioned, we're aiming to enroll 7,500 vehicles in that pilot. And then the last pilot I wanted to call out that wasn't on my original list, but it's another epic pilot is called the Smart Meter Connect. And so what this pilot is trying to address is that often when customers want to install a level 2 charger, it requires them to upgrade their panel, which can then trigger service or distribution upgrades. And that's costly for the customer, for the grid. It usually deters EV adoption and takes a lot of time. And so with this pilot, we want to test the ability of a smart meter to orchestrate the load, the EV charging load at a customer's home. So instead of necessarily a third-party software, it's the meter itself that is able to orchestrate EV load and therefore defer or prevent the need for a panel upgrade or a service upgrade. So it further encourages EV adoption, avoids additional costs for the customer, and allows kind of more dynamic use of energy at the customer's home. So with that, I'll end and I'll hand it back to Jingjing.
Thank you so much, Sarah, for the overview of PG&E's pilot portfolio and alluding to the future. Very interesting and exciting. So if you have any questions for Sarah, please enter your questions in the Q&A box, and we will transition to our second speaker, John Taggart, President and founder of ViewGrid. Please, John.
All right. Thank you, everyone, for having me, and was really appreciative of the opportunity to come speak to you all. I'm going to speak a little bit about our company, ViewGrid, some of the work we're doing with our utility partners, including PG&E, and sort of why that matters. What's the value and the benefit of doing this work? So ViewGrid is a software company. We're based here in San Francisco, started about 6 years ago. Really built to build the digital infrastructure supporting electric vehicle grid integration. So we want to help accelerate the decarbonization of transportation and feel like we can do that by bringing together the utility sector that, as Sarah mentioned, is now responsible for fueling these EVs with the automotive and charging world, with sort of the software revolution that's happened here in the Bay Area. Our company really reflects this in its DNA. So we have people on the team. We have about 80 people in the company. People coming from software companies as well as automotive companies and utilities. And equally in our investors. So we've gotten venture investment from climate investors, growth investors, software investors, but also most recently strategic investors as well. Received some funding recently from the growth arm of Toyota Motors, Woven Capital. We've been really fortunate to work with utilities across the country and sort of help support them on their electrification journey. So what does our software do? So really, we're trying to build that bridge between all the different parties that need to be aware and have some element of control and visibility into what's happening with charging. So for us, the software we build helps support both EV drivers. So if they want to sign up for a utility program, if they want to sort of understand their charging behavior, if they want to sort of make adjustments, we have a tool for that. On the utility side, we have a tool for utility program managers trying to run analyses and experiments and sort of see how their program's performing as more and more customers sign up. And then in the middle, we have the system that connects to the devices themselves. So that's both on the grid side, so where we build integrations with the utility and their IT system, but then the specific chargers and automotive telematics vehicles, so the onboard control systems that vehicles have today. And that allows us to get visibility and control of charging. So Sarah mentioned a pilot we're doing with PG&E called the EV Charge Manager. Really excited to work on this with their team. As Sarah mentioned, this is really focused on trying to address grid infrastructure constraints So when we built out the electric grid, when PG&E built out the poles and wires and substations and transformers, there wasn't the expectation that we would have this EV load in addition to the building load. Most of the load there for residential, is for your air conditioning and for your heating and for cooking, lighting, etc. But now we're adding this new pretty high power load to that system, and that's creating some stress. And so we're working with PG&E to develop ways to reduce that stress on that infrastructure, so that we can avoid having to spend billions of dollars sort of upgrading the full system, and can be really targeted in where that spending takes place. So we already have several thousand EVs enrolled in that program. If you're in any of those 3 counties mentioned, you can sign up today. If you have a Tesla, if you have one of the chargers that we support, that's something you can do and receive a benefit. So, mention what's the challenge here. So PG&E is really at the forefront of EV adoption. California has about half of the EVs in the country. And that sort of EV growth, as mentioned, is starting to strain that system. So if you look at the power requirements of EVs, a lot of that is concentrated at home. So most charging takes place at homes, mostly single family homes today. Hopefully that will diversify. A lot of it takes place at pretty high power. So if you think of an average home uses about 1 to 2 kilowatts over the course of a year. They might peak at 5 or 6 if they're running their air conditioner. EV charging can take place at level 2 charging, as we call it, can take place anywhere from 6, 7 kilowatts up to 20 kilowatts. So it's a really high power load. And this is happening in sort of neighborhoods where EV adoption is correlated. So you tend to see people adopt EVs where their neighbors adopt EVs. So while the system can support that today, as that continues, that's going to create more and more stress on that system and create reliability challenges or require significant capital investment by the utility to make sure they can support that system. So what are we doing to try and help? So what we call distribution integrated smart charging orchestration, or DISCO. This is really our technology for trying to address this challenge. So rather than only coordinating charging based on sort of avoiding that 4 to 9 p.m. period and that bulk system peak, we're really trying to localize and optimize based on what's happening in that vicinity. So if there are other vehicles charging on the same transformer, how do we make sure that we don't see coincidence of charging in a way that will exceed the asset limits or sort of make those transformers degrade faster or have reliability problems. So if you're enrolled in this program, you would come home, plug in, and rather than immediately charging, we would be sending a schedule that allows your vehicle to still reach its full state of charge that you desire by the end of your evening or the morning when you need to depart. But we find the time that is best for the grid in coordination with all the other vehicles that are on that system. So here's an example for a feeder. So these graphs, each of the different colored bars are individual EVs. So the gray base load on the right, that's all the other electricity usage. But all the colors are individual EVs. You can see them kind of arriving at home. They charge for some number of hours, depending on if they've gone pretty far that day and need to charge up a lot, or just need a little bit. And what we found is we can reduce the load on that sort of distribution asset, in this case, a feeder, by spreading that charging out. And that can occur whether we have specific information on what's happening with regards to other loads, or even if we don't have that grid awareness, we can still spread it out and reduce the impact quite substantially. So why does this matter? If you look at California, there have been a number of studies on this. This one's from the Public Advocate's Office, the CPUC, sorry. And pretty much all of them come to the conclusion that managed charging specifically can lead to billions and potentially tens of billions of cost reduction if done right. So if we can take this load and really make it flexible in the way that Sarah mentioned, that can be a really big asset for that grid, and ensure that we keep rates at reasonable levels, that we don't have to go and upgrade the system to such an extent that it causes affordability challenges. So we're really excited to work on this with PG&E and our other utility partners. And I think it really matters. So this isn't just a research project. This is something that I think really needs to grow and scale and be a critical part of the electricity system. So thank you.
Thank you very much, John. Appreciate your covering Beaver Grace solution and really stressing the value of EV charging on distribution grid capacity management. So with that, we're going to transition to our third speaker, Laurent Schmidt, Head of Utilities for DC Bell. Laurent, you're up.
Yes, good morning to everyone. So I'm going to present now our DC Bell activities into the EV charging integration space, particularly into the residential environment. Just trying to... So basically, Decibel, we are a Canadian-based company, and we are launching a new generation charging station for residential home, particularly focusing on to bidirectional charging into residential environment, as what we just heard. So we focus into integrating bidirectional charging in homes together with solar and standalone batteries, potentially, and while also considering real-time data exchange with utilities from the grids, as well as potential virtual power plants being interested into proposing energy program into such home environments. So what we've seen is actually, if we rethink this system from A to Z, this requires to rethink basically the architecture of energy system in residential environment, and particularly trying to connect all what goes with DC under DC. So the DC charging of cars together with PV and battery in order to be more efficient into power conversion into the home environment. But it's also raised a big question on what type of edge calculation you need to do to optimize this charging and discharging for the benefit of the consumer together with real-time price signals or time of use signals received from the grid side. So we've decided to design, I would say, a new home energy station hardware, which you can see here, which we currently launch in California through different deployment program, which is actually a home energy station which combines a large sets of functionality, including, of course, power conversion from solar, being able to charge bidirectionally with the car, but on the top of that, also being able to trade, store, buy, charge, and prioritize, forecast, and manage the charging and discharging of electricity for the car, and in coordination with the rest of the home, in view of these price signal received from the grids and virtual power plants. So that's basically where we are at. We think this device is going to become a new edge device into the home environment. It will interface directly with all the major home appliances, such as heat pumps or water heating systems, and others in order to be able to orchestrate energy at the house level and act as a data interface with the higher level DERM system from the utility or virtual power plant operator. So what we've been working on is beyond these architecture hardware level is also to rethink the way to interface these various environments. So as you can see, this interfacing is not an easy interfacing because you see a large set of actors interested into interacting with the charger, actors such as basically utilities operating their DERMs through energy program as introduced by John, but also virtual power plant operators and others wishing to offer different kind of programs to link with the ISO, the CAISO real-time price signals as an example, or different emergency load reduction programs and others, which needs to interact with the local energy management into the home environment. So really what we had as a target introducing the Decibel Home Energy Station is to bring analytics and hedge optimization, being able to compute and run all these real-time data exchange and make at every minute the smartest decision for the benefit of the consumer. So we really focus on to maximizing benefit for the consumer charging. What we think is that to be able to do that, we need to have a real-time end-to-end situational awareness environment, which allows, of course, to plug in with all the sensors in homes, with the car itself, and bring real-time data to the various actors of the energy value chain. So, of course, the consumer itself through an app, through his whatever watch, and through the home energy station itself, which plays a central role in orchestrating the local home energy ecosystem, and as well as basically being able to operate a technical aggregator environment and offer basically the option to connect with various energy programs and virtual power plant service provider. That means that I would say in parallel to the introduction of this software environment and the hardware, we are working on the creation of a marketplace, which is able to facilitate connectivity between the consumer and these various actors interacting into this vehicle-to-grid integration ecosystem. And really what we focus on is making sure that our hardware focus the highest fidelity, flexibility transaction to utilities and virtual power plants operator, and in the same time, basically guarantee a seamless user experience. So at the end of the day, consumer wants their cars to be charged when they use it. So they must be able to opt out and fully control the complexity of some of these energy programs. So the consumer interaction is really a strong attention into the delivery of our hardware environment. So basically, our hardware is offering open APIs, which are capable of computing and aggregating a crucial set of data with the consent of the consumer back into the utility environment or DERMS, virtual power plant operators, such as real-time baseline forecasts, digital twin calculation of what would be the behavior of the home energy station in view of various real-time price scenarios, local PV forecast conditions, as well as being able to receive complex utility control, either price-based through a data exchange standard like OpenADR3, as well as direct power set point level if we are more into emergency load reduction programs, while providing critical power measurements because the hardware itself integrates its own sub-metering sensors, which can be used into the settlement of these associated programs. So very happy to respond to any question which you may have. Chat. Thank you.
Thank you so much, Laurent. Thank you
and
for.
Sorry for the bad connection again.
No worries. That will work out fine. And yeah, thank you for walking us through the complexity of the bidirectional charging ecosystem, the solution that Decibel offers. So let's welcome our last but definitely not least speaker, Zachary Lee, Director of Research and Development of PowerFlex. Thank you, Zach. Please, stage is yours.
Thank you, Jingjing, and thank you for the previous speakers. Those have been absolutely fascinating presentations, and I hope I can live up to the standard you all set. What I want to talk about to you all today is how we can orchestrate all the behind-the-meter distributed energy resources, especially EV charging, and looking at more from a commercial and industrial setting. So my name is Zach Lee. I'm Director of Research and Development at PowerFlex. At PowerFlex, our mission is to enable organizations to meet their sustainability goals by providing intelligent on-site solutions. And we do that in three main areas. The first is managed EV charging. We have over 32,000 EV chargers that we actively manage. This is one of our examples. At LAX, we have over 1,200 EVSEs. Those are what we know as charging stations. Scattered around the various parking garages to allow people to charge their vehicles while they're traveling. We also are the #2 installer of commercial solar in the United States. We have over 450 megawatts of commercial solar installed to date. This is just one example of a warehouse in California for Amazon where we have 3.8 megawatts of solar installed. And we also provide stationary storage. This is an example at the San Diego Zoo, where we installed a 1 megawatt, 4 megawatt hour battery to help the zoo manage their demand charges and other things like that. So we kind of, our offerings kind of span those technologies. We also go anywhere from turnkey building projects to managing projects that are already in the ground with our software solutions for monitoring and control. So I want to focus first on the EV charging use case. This is just a couple of examples of the types of customers we work with. Municipalities, universities, schools, and hospitals are a big one. Multi-unit housing, so this is apartments and condos, airports, as I mentioned, workplace charging, as well as fleets. And so as we talk about EV charging, I want to kind of run through a scenario with you. So imagine you are a facility manager and you've been tasked with installing charging at a workplace for employees. And so you do a survey of your on-site electrical infrastructure, and what you realize is, as our previous speakers have discussed, systems weren't designed to charge EVs, and EVs can be a major load. And so what you might find is that you can only install a handful of EV chargers at your site. Let's say you can install 6. But you do a survey of the drivers already at your facility, and there's already 12 EV drivers at your office. And you know that once you install EV charging in an office setting, more drivers are going to want to switch to EVs because they have access to convenient charging. And so that is a problem because with conventional charging, you can only install those 6 chargers. And so traditionally, the way you might address that problem is one of 2 ways. One is to implement a wait list. So you might ask drivers, if you show up and there's an open charger, great. If not, join this wait list. And once someone who arrived earlier in the morning gets done charging, we're going to send them a notification. We're going to ask them to move their vehicle, and we're going to have you go and move your vehicle physically to that charger. Now, that's a huge waste of time. It's also expensive if you think about the lost productivity of drivers needing to physically move vehicles. Another thing that we've actually seen with some technology companies and things is they'll actually pay valets to spend their days shuffling vehicles around so that vehicles get charged with limited infrastructure. And we just think that is a huge waste of resources. And so there is a better way. And that better way is through using load management technologies, so that we can install a charger in every parking space. So our vision is that every parking space where you leave your vehicle for an extended period of time will actually have a plug for you to plug in. And then we can use software to decide when your vehicle charges over time to make sure you get the energy that you need by the time that you need it. And the reason we're able to do that is because drivers have a ton of flexibility. So the average driver, in our experience, needs somewhere between 10 and 20 kilowatt hours per day. And if you look at this example, this is actually a shortened day. Let's assume that this driver needs to get to a meeting across town at noon. They need to leave at noon. So even with just that 4-hour window, with even a moderate power level 2 charger, she only needs to be able to charge for about an hour and a half. And so we have all this flexibility. We can charge her early and free up capacity later. We can spread that charge out over time, or we can do something interesting with it, depending on the needs of the site. And what that allows us to do is really improve our infrastructure utilization. So we can spread that charging out, considering the needs of each driver about when they need to leave and how much energy they need, and run an optimization so that we ensure that we get all those drivers' energy needs met while staying below local power limits. And so I want to walk us through an actual case study example. This was actually our first site at Caltech. This is a parking garage there. And what we were able to do there is install 720 kilowatts of level 2 EVSE capacity. As you can imagine, most parking garages don't have an extra 720 kilowatts of capacity available. And in this case, we were able to do it by installing 250 kilowatt transformers. So if you run some back of the envelope math, that's about double the number of chargers you should be able to install without load management. And this is all allowable because of the National Electric Code. So there's a provision in the National Electric Code that says that any EVSE needs to be allocated its full power capacity as if it's a continuous load, unless it is controlled by a software automatic load management system. And if you have that load management system, you can actually use the limit of that load management system when you're running your calculations for ensuring that you have enough power on site. And so that's what allows us to do this kind of at sites across different industries and across the country. Now, once we have controls, we can go beyond just optimizing around local infrastructure limits. We can also respond to price signals, and we do that in a couple of different ways. We can shift load from on-peak to off-peak periods. We can also reduce peak demand, which reduces our demand charges. We can participate in demand response programs, things like the Emergency Load Reduction Program in California. And we're really excited about some of the dynamic pricing pilots that PG&E and SE and some other utilities around the country are rolling out because those give us even more signals to optimize around. This chart here on your right is an example of one EV tariff. Here you can see that demand charges can be a huge problem for EV charging infrastructure. But with load management, we can significantly reduce those demand charges by about 75%, which is hugely valuable. But we can do more. And we can do more by integrating additional distributed energy resources. So I want to walk us through another example. This is a site where we actually install not only EV charging, but also solar and stationary storage. And let's see how integrating and orchestrating those technologies can allow us to save operational cost as well as capital cost. So first, let's look at what happens if we would have just installed regular, dumb, unmanaged EV charging. What we see is the gray here is the building load without any additional technologies. And if you add that orange slice, that's the EV load when it's unmanaged. And what you see is we set a new demand peak in the early morning when everybody's arriving at work. But with load management, we can actually adjust that EV load through time, adjusting to the building load over time, and actually significantly reduce our peak demand. That's helpful for a demand charge reduction. It's also helpful for the grid that now doesn't have to respond, doesn't have to meet that peak demand. But we can go further. So if we add solar to this site and we add a stationary battery, what we can actually do is first generate clean on-site electricity, and then through load management, shift EV charging load into the middle of the day where it can use that on-site generation. And then we can also use stationary storage to absorb that green energy in the middle of the day and shift it into the on-peak period, which is generally this 4 to 9 p.m. period now in California. That's a time when there's when the energy rates are extremely high. It's also a time when the grid is extremely stressed. So we're able to both save money for this customer by introducing these technologies and be a better citizen of the grid and enable electrification at scale. So with that, I want to thank you, and I think we'll maybe have some time for questions.
Thank you so much, Zach. I want to thank all of our speakers for your super informative presentations today. I hope everyone have been finding this session very useful and interesting. I know we're still kind of early in the event, and maybe people are still getting around using this platform. I don't see any Q&A questions in the Q&A box. Feel free to enter anything here. We still have 1 or 2 minutes left, but I think question to our event organizer, do we also have ability for people to ask questions verbally here? If so, we may have time for 1 or 2 questions.
There's a question in the Q&A.
Great. Okay. Is residential or commercial the best opportunity for EV load management? Yeah. Thanks for that question, Marco. I think that any of our speakers want to take on that, share your perspective.
So I'll start by saying I think it's complicated. I think the bulk of the charging right now takes place in residential, and that's where a lot of the dwell time is, and so there's a lot of flexibility there. However, a lot of the higher cost charging or sort of higher infrastructure cost often happens in commercial settings as well. So there's a lot of value in making sure you're doing smart things there too. Zach, I don't know if you want to add to that.
Yeah, I mean, I think it's a both and solution. We're always going to need charging at home. It's a very convenient use case. I think there's a ton of value in any type of daytime charging. That's when we have access to solar. So whether that's workplace, school, if you're work from home, then charging your vehicle at home, all of those scenarios where we can shift load to take advantage of solar, especially on-site generated solar, is hugely valuable.
Yeah, absolutely. I would just, add to that it really depends on your goal, and the utilities and grid situations are different across different parts of the country. In California, we have that, evening peak issue. So residential load profile tends to align with that. So that's certainly important to tackle. Other parts of the country or individual customer may have bigger need to absorb renewable, and that some of the commercial large projects could really help address that. So yeah, these are all important sectors. Let's try just take some. Brian also asked any potential for peer-to-peer energy trading on these platforms.
That's a regulatory challenge, I would say. There are people doing it in different jurisdictions and things, but it is challenging. There is an interesting use case of bidirectional charging for energy trading. I come with a full battery, somebody else needs energy prices from the utility are really high. Could I discharge my battery, feed into the system, charge their battery, and then there be some kind of settlement there? I'd say we're in very, very early stages of a system like that, but it could be very interesting.
Yeah, I think one thing to keep in mind, if you think about trading and sort of peer-to-peer type relationships, you're still relying on the network. You're still relying on the grid to trade that power, and so there's a regulatory decision of like, how do we pay for that, and how do we ensure that system continues to operate. But today I don't see a lot of that.
Great, thank you. Well, I think we should close here and let everyone transition to the next session, but let's thank our speakers once again. Thank you for walking us through this fast evolving landscape, and your excellent illustrations, graphics are super helpful to help us understand the complexity here. So we look forward to following up with anyone interested. All right. Thank you, everyone. Enjoy the rest of the event.